Hey guys, this video for calculus is a continuation of 2.1, and for pre-cal this switches over to 2.2. This is going to continue talking about derivatives. Last video and lesson we were talking about derivatives as a slope and as an average rate of change. We're going to start to make the transition of finding the actual specific rate of change at one moment. Okay, so I will actually bring back the paper and refer to last class's notes. Make sure you've watched that video if you haven't. So let's start off with some of the notations you're going to see. We've talked a lot about the fact that derivatives is a synonym for slope. Okay, the only difference is in the past, slope we could only find for linear functions. Derivatives we'll be able to find for any function. So a derivative, a slope, is a change in y with respect to a change in x. Some new symbols you're going to start to see, which we talked about last class, is delta. Delta means change. So it's a change, delta y over delta x. Another notation you're going to see is instead of the triangle for delta, you'll see the letter D, dy dx. And then the most popular notation is f prime. So if I have a function, just f of x, it'll represent what the actual function looks like and where you can plot some points. But the moment you put that prime, it starts talking about the rate of change of that function. These two here, dy dx and f prime, are the two most popular that you will see in Cal, in AP, and so on. Okay? So now what we're going to learn today is called the limit definition of a derivative. This is a lengthy process, so today's going to feel a little lengthy, the work at least. But the good news is, starting next section, you're going to learn shortcuts for this. And in the AP, you are allowed to use the shortcuts. Now, the way that they try and stump you in the AP is that they'll give it to you in this format. And your job is to make the connection that this just means the derivative, find the function, and then you can use the shortcut once you determine who the function is. So let's start off by analyzing what this means. It says the derivative, okay, because remember f prime means derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Now, before I go on to all of this verbal explanation, I'm going to bring back the image I drew you guys last class, okay, to explain to you what that formula means. So last class we had this image, okay? We said that f of x plus h minus f of x over h was just another way of writing slope, okay? Now, so this part is old news. What's new news is this limit as h approaches 0. Well, let's see what h was here. When we talked about this last class, h was the distance between the two x's. So what they're saying is that as the distance between the 2 points on the graph starts getting smaller and smaller, and the distance starts approaching 0 between the 2 points, you're going to get a more exact slope. So for example, if I wanted to know what the slope was in this area, remember how we said here, like it's obviously positive, and then it starts going to 0, and then it starts going negative. So when I test these 2 points, I'm going to get an estimation of what the slope is. But let's say I start using just these 2 points. Now I'm going to get a much closer estimation. Now h became smaller. The distance between the 2 points became smaller. If the distance between the points became 0, you are technically, instead of analyzing 2 points, you are just analyzing 1 point, and I will get the actual derivative, the actual rate of change of that one specific point. All right, so that's why that limit portion comes into play here. All right. So now, some reminders from last video. Some textbooks will use, instead of h, they'll use delta x. Because again, delta x is the change in x. I like using h because being that this process is going to get lengthy, it's a lot neater to see just a simple h in your work instead of these delta x's mixed in with the x's from the actual function. All right. So using this formula is going to give you the derivative. Usually it's going to be a new function. Most of the time it is. And that new function pertains to the entire function at any given point. So again, when you do this work, you'll get a new function as your answer. Plugging x's into that new function will tell you the actual specific slope at any given point within the function. Okay, so you can solve for this and then plug an x in, and now it'll give you the slope at that point instead of the location at that point. So the difference between, let's say, f of 2, if I plug in 2 into an actual function, it'll give me the location, the y value. If I plug a 2 into here, okay, if I plug a number into there, I'm finding the derivative, the slope at that point, okay? So again, stay hopeful. Today's lesson, the work is lengthy, but next section you are going to learn some shortcut rules for this process, and it'll make this a lot easier. All right, so let's go straight into our first example. And because the work is lengthy, I'm going to try and color code as much as I can for you. So this says find the derivative of f of x, which is 2x minus 3, using the limit definition. So I'm first going to show you, here I said you usually get a new function. I'm going to show you that rare scenario where you don't get a function first, and then we'll go into the more complicated ones, okay? So I need to start off by writing that f prime of x is equal to the limit as h approaches 0 of, let's scroll down a little bit, f of x plus h. Remember how if I said f of 2, it just means I plug a 2 into the function? That just means anywhere that there was an x, I need to put an x plus h. So I'm going to rewrite this entire function, and anywhere there's an x, I'm going to put an x plus h. So I'm going to say 2 instead of x plus h, and then minus 3. Okay? So that right there, if I'm color coding, this is my x plus h portion, my f of x plus h. Now I have to say minus f of x. F of x is just me rewriting this entire function. Now, something very important is every time you do this step, you have to put parentheses because this negative applies to the entire thing. Okay? So here's my second part. So you just did, in purple here I underlined f of x plus h minus, and then in green I wrote the entire function f of x. And this is all over h. Okay? So we will say that step 1 is to plug into the formula. Step 2 now is going to be to clean. Okay? So when you clean, I'm going to distribute this 2 and distribute this negative. So I'm going to bring down my equal sign. I have to rewrite this limit portion up until I plug in that 0 for h. Now, if I plug in a 0 for h right now, I'm going to get a 0 in my denominator, which is either going to be an indeterminate or undefined, okay, which is going to give me an error. That's why I have to clean before I can plug in that h. So I'm going to have 2x plus 2h minus 3 minus 2x plus 3 all over h. Okay? Now, I'm gonna write you some notes in a moment here on the side. I'm going to talk you through them first. A nice way to remember things is that in these limit definition formulas, the original function will always cancel out. So a 2x and a 3 should always cancel out. And you can see I have a positive 2x and a negative 2x. And then I have a negative 3 and a positive 3. You see how the original canceled out? So my next step is, I'm going to rewrite it, see if I can clean anything else out. Okay? So you can see that these h's cancel out. And I'm left with the limit as h approaches 0 of 2. Okay? Now, I do not have an h left to plug in, but hopefully you remember from our limits chapter that the limit of any constant is just that constant, which is 2. Okay? So let me draw a quick connection for you. If we said that this formula is the limit definition of a derivative, and derivative just means slope, so my answer told me that my slope was 2. This is a linear function, which means I can find the slope the easy way. Y equals mx plus b. right? Here's my slope, and here's my y-intercept. You can see that my slope was supposed to be 2. Now, you're going to say, why in the world did I do all that work if I could have seen my slope was 2? You won't end up doing one for functions this simple. I just wanted to walk you through the process with an easy function. But the whole point of this formula is that now, once I go to something beyond a linear function, I can still be able to find the slope. All right? So I'm going to take a moment and write you the steps here, and then I'll have you copy them down, and we'll continue on to another example. All right, so let's check out these steps I just wrote for you here. So step 1, we plugged in the formula. Okay, so the x plus h into the formula, to the function, I'm sorry, and then minus the original function all over h. Then we cancel the original. Then we canceled out any h's. And then we plugged in the limit. Okay, so let's see what that looks like when the functions start becoming a little more complicated, bigger than a linear function. All right, this next example says find the derivative of f of x equals x cubed plus 2x using the limit definition. So we just went from a linear to a cube function. So step 1, f prime of x equals the limit as h approaches 0 of, I'm going to rewrite the function, but everywhere there's an x, I'm going to put x plus h. So I need to say x plus h cubed plus 2 times x plus h. Okay? And then minus f of x, which is minus the original function. Okay? So if we're color coding like we did last time, this portion is the f of x plus h, and this is minus the f of x. Okay? And then, of course, all over h. So step 1, we plugged in the formula. Step 2, actually, I should have written a step in between there that says to clean. I apologize for that. We definitely have to clean this first. This cubed is going to take us a moment. I'm going to take a moment and do it here on this side, okay? So remember that x plus h cubed is the same as saying x plus h being multiplied 3 different times. So x plus h times x plus h times x plus h. All right? So you're going to FOIL 2 at a time. X times x, x squared, x times h, another x times h, and then h times h. Okay? This is going to get multiplied with the last x plus h. Okay? I am going to combine these two to say x squared plus 2xh plus h squared. Okay? So now x times all 3 of these. And then h times all 3 of those. Oh, I'm running out of space. There we go. Now, I'm going to combine any like terms. It's going to be a little hard to see. These two both have a single h and an x squared. I don't have any other of these x cubes and these h cubes. So I'm going to say x cubed plus, there's 3 x squared times h. And then a single x with an h cubed. There's a total of 3 of them. Okay, so I know that was a little lengthy, but all that was just to clean this first part. So now I can say the limit as h approaches 0. This portion becomes all of this. Now I have to distribute this 2. And then distribute this negative. Okay, so bear with me. I know this is looking messy. Everything up until this 2h is me just cleaning this first portion. And then this was me just distributing the negative of the f of x. Okay, and all of this is still over h. So remember the next step that I told you is that the original will always clean out. So I'm looking to cancel out an x cubed. I have a positive x cubed here and a negative x cubed here. And then I have a positive 2x right over here and a negative 2x right here. If that doesn't happen, that's a good red flag that you made some sort of mistake. So always check that out. All right, so now I'm just rewriting everything that got left behind. And if you look at each term, they each have an h left behind in it. So I'm going to be able to take, I'm allowed to take one h from each term. So 1 from the denominator. This term only has 1. I'm going to take it. This one has 3. I'm going to leave 2 behind. I'm only taking 1. This one also has 3. I'm going to leave 2 behind. And this one has 1. Okay? So let's rewrite what we're left with. I have a 3x squared plus 3x h squared. I was left with 2 there. Plus h squared. I was left with 2 there. And then plus 2. And I was left with nothing in the denominator. Okay? Very last step is to plug in that limit. That means I am plugging in a 0 everywhere there's an h. So I'm plugging in a 0 here and a 0 here. So now that I'm plugging in the limit, I do not have to write this part anymore. So I can say 3x squared plus 3x times 0 plus 0 squared plus 2. A good rule of thumb is to realize that any term that has an h is going to get canceled out. Okay? So my answer to this is 3x squared plus 2. Okay? So I told you when you use this formula, you were going to get a function as your answer. So if I use f of x, let's say if I do f of 2, okay, let me show you the difference. F of 2 is me plugging 2 into the original, which would be 2 cubed plus 2 times 2. Okay? And then if I did f prime of 2, it would be me saying 3 times 2 squared plus 2. Okay? So 2 cubed is 8 plus 4. This answer tells me my location. Okay? Here I got 4 times 3 is 12, 13, 14. I get 14. This, because it's derivative, it has a prime, this tells me my slope at x equals 2. So you can see the difference between using the function at a certain point. This will tell me like my y value to be 2 comma 12. And then using the f prime, what I found here, tells me my slope at that value. All right, so the next thing that I want to show you is how this looks visually as a graph. And this is something that we will go much more into depth in Chapter 3. I just want you to start getting an idea, and please feel free to use desmos.com/graphing or /calculator, I believe it is. Just put it in Google and it'll come up. And always put in your original function into your first equation and then your derivative into the second one. And you can see the relationship that the graphs have with each other. So one thing you should be able to always catch is that the derivative's exponent will always be 1 less than that of the function you started with. So if I start with a cube, I should end up with a squared. And then if my next term was to the first power, my next term in the derivative should have no exponent, no variable with an exponent. So it goes from 3 to 2 and from 1 to none. It always goes down 1. Which means that if my image for the original function is a cubed, yes, and if you're in my class, we talked about this being the robot, then you should be going down to a squared, which is the u, okay? Another thing you can catch is if this is my function, you read graphs left to right, my rate of change from left to right is always going positive. Therefore, my slope function, my derivative, is always positive, also known as being positive. Y values would always be above the x-axis. Okay? So let me show you what that looks like for the first question we did. Okay? So here my original function was 2x minus 3, which is a linear function. Okay? Linear functions reading left to right are always positive. We said that the slope here was always going to be positive 2. So you could see that for my derivative function, the value is always a positive 2. And again, I don't want you to stress about the graphs. It's something that you're going to start seeing little by little that you will get much more of in the following chapter. All right, guys, last thing for today. There's this big fancy word. It's differentiability. All it is, it's a fancy word for saying the ability to have a derivative, okay? So it says a function is differentiable, able to have a derivative, if it is continuous and has no sharp turns. So we had said that something is continuous if it has no holes, asymptotes, or jumps. So if the question is ever asked as to whether something is differentiable, it is differentiable only in the locations where there is, it is only not differentiable in the locations where there's a hole, asymptote, jump, or sharp turn. So let's look at this image that I drew for you here. I have a linear function going straight. I hit a point and I sharp turn and I curve, yes, parabolically. Then I have an asymptote. I should have an arrow down here. Then I curve up, I jump, and then I go to a linear function again with a hole, and then I keep going. So the statement could be said that this function is differentiable everywhere except, and the reason I write it like that is because this function is differentiable. It can have a derivative. It can have a slope here. It cannot here at -2 because it has a sharp turn. It can have a slope, a derivative in all of these locations. It cannot at 0 because nothing exists. It should make sense that I can't have a slope where there isn't a graph, okay? So I can't at 0 because there's an asymptote. Then here I can have a slope. It goes positive upward. And then at 2, I do not have a slope because I have a jump, okay? And then here I do have a positive slope. I have to skip counting number 3 because there's a hole. Nothing exists there. And then I continue having a slope, a derivative. So again, differentiability is just a fancy word of the ability to have a derivative. So a function usually is differentiable everywhere except where there are holes, asymptotes, jumps, and sharp turns.